All right, welcome to This Explainer. Today, we're doing something absolutely crucial. We're drawing the boundaries of your code. We're talking about object-oriented programming, and specifically, we're diving into the security gates of OOP, Access Modifiers. We really need to figure out what data should be totally open to the public and what needs to stay completely hidden in the vault. So, let's jump right in. Picture this. It's a total nightmare scenario. You open up your banking app and there is zero security. Literally anyone or any other part of the program can access your account balance directly and just change it to whatever they want. They could just run a line of code saying balance equals negative 5,000 and bam, your money is gone. Terrifying, right? Well, this is exactly what happens when we don't set strict boundaries in our code. Here's a quick look at our roadmap. First, we'll cover OOP security and encapsulation. Then we'll break down public access, followed by the private hidden vault. After that, we'll get into the tricky ones, protected and default access. And finally, we'll wrap up with an exam mode featuring mixed questions. Okay, Section 1, OOP security encapsulation. In the programming world, we literally have to build walls around our sensitive data. By definition, encapsulation is the practice of bundling your data, your variables, and your methods together inside a single class, strictly restricting direct external access. Think of your class as a high-security building. Unauthorized personnel can't just walk off the street and straight into the vault, right? They have to go through the proper, authorized channels. So the whole concept really boils down to control. Think about an insecure setup where an external source can directly change a bank balance to a negative number. That's a total disaster. Secure code, on the other hand, uses specific methods, like a deposit method, to control that balance. These methods act like security guards. They check the ID, validate the transaction, and make absolutely sure no one is trying to, deposit a negative amount of money.
Moving right along to Section 2, Public Open Access.
Now that we know why we need security, let's look at the actual tools we use to enforce it. The lowest clearance badge in our security system is the public modifier. When you label something as public, you're basically saying the front doors are wide open. This is the widest access level, meaning the data or method can be accessed from literally anywhere in the entire program. And that's great for general behaviors that the outside world absolutely needs to interact with, like a login or a show information function. But a quick warning here, never, ever use public for sensitive variables, because, well, that's exactly how you get your bank balance stolen.
Section 3, Private, Hidden Vaults.
So if public is the open lobby, where do we actually put the sensitive stuff? Think about the stark contrast here. Public is that open lobby where anyone can walk in, read the brochures, and write in the guest book. But the moment you make a variable private, you instantly shut out the rest of the application. It acts as a hidden vault, restricted completely and entirely to the class itself. No one outside the class even knows it exists. But wait, if it's completely locked away, how do we actually use it? This is where getters and setters come to the rescue. And listen up, because this is the exact 3-step process you're going to need on your exams. First, make your variable private. Second, create a getter method to safely read that data. And third, create a setter method packed with logic rules to write the data safely. Your setter is basically the bouncer, making sure nobody tries to set an age to, say, -20. All right, let's put this to the test. Here's a classic exam question you're very likely to see. What happens if you try to directly modify a private variable from outside its class? Does it A, successfully update? B, is it just ignored? Or C, does it throw an error? Go ahead and lock in your answer. And it's C. It throws an error. The compiler acts as an uncompromising, strict security guard. If it sees outside code trying to touch private data, it stops the whole program dead in its tracks and throws an error to protect that vault. All right, Section 4, Protected and Default Access. So, we know public is wide open and private is totally locked down. But what about the middle ground? Let's talk about the slightly more nuanced security levels that professors absolutely love to test you on. First up is the protected modifier. Think of this as VIP clearance. It grants access to classes within the same package, but more importantly, it grants access to child classes through inheritance, even if those child classes live in a completely different package. It's honestly perfect for sharing safe data down the family tree while keeping the general public out. Then we have default access, which is sometimes called package private. This happens when you don't write any modifier at all. Now, leaving it blank isn't a syntax error, but it does create a very specific boundary. It basically means the data is accessible only by classes living on the exact same floor, meaning the exact same package. It can be a little risky because you might accidentally create this access level just by forgetting to type the word private. Okay, I want you to take a mental screenshot of this matrix right here. This access level breakdown is literally the ultimate cheat sheet for your finals. Think about how the access scales up. Private is only the same class. Default adds the same package. Protected adds subclasses into the mix. And public just says a big yes to everywhere. Seriously, burn this into your memory. Let's test that memory right now with another interactive quiz question. Which modifier should you use for a method that only child classes should inherit and use? Is it A, private, B, public, or C, protected? Try to apply what we just covered on the cheat sheet. The correct answer is C, protected. Remember, if you chose private, you'd block the child classes completely. If you chose public, you'd let absolutely everyone in. Protected is that perfect VIP middle ground that brilliantly balances security with the needs of inheritance.
Section 5. Exam Mode Mixed Questions.
Let's dive into the final stretch with some rapid-fire exam questions that you're definitely going to see on your tests, combining all these concepts. First scenario. What is the primary purpose of a setter method in encapsulation? Is it A, to make data public, B, to securely control and validate data changes, or C, to bypass the constructor? The answer is B. Remember, setters are the bouncers checking IDs at the door of your class. They exist entirely to securely control and validate data changes. They are the exact logic that stops someone from depositing a negative amount into that bank account we talked about earlier. Let's do one final fundamental question to make sure the core concept of this entire explainer is totally locked into your memory. What best defines encapsulation? A, sharing data freely between classes, B, direct data access, or C, accessing data strictly via class methods? Yes, it's C, accessing data strictly via class methods. This simple rule is the absolute foundation of object-oriented programming security. Honestly, it's what keeps massive software applications from just falling apart under their own weight. We've covered a ton of ground today, from the open lobbies of public access to the hidden vaults of private data. I want to leave you with a provocative thought to apply to your own work. Think of the code you're writing right now as a building. Have you been leaving your vault doors wide open by using public everywhere just out of convenience? Well, it's time to review your projects, draw your boundaries, and lock down your data. Keep coding securely, and I'll catch you in the next explainer.